This lesson on resistance, current, and Ohm's law is broken into two parts. In the first lesson, we'll focus on Ohm's law, and in the second, we'll focus on electric power and AC versus DC currents and voltages. All the images you see in this video are attributed to OpenStax College Physics, which is a text published by openstax.org under the Creative Commons Attribution License version 4.0. Electric current is the flow of electric charge through some material or through some medium. And usually we're in physics, we're focused on electric currents flowing through solid state matter like wires, conductors, copper wires, aluminum wires, that sort of thing. So in the solid state, electric current is carried by electrons because the protons are much too tightly bound in the nuclei of their atoms to move around in a wire, but the electrons in a conductor are relatively free to move. So if you apply a voltage or an electric field to a conductor, this will motivate the electrons to start moving. Now, the thing about electric charge is that, well, first, it's defined as the amount of charge, Q, flowing through a cross-section of a wire, indicated by A here, per unit time. So it has units of coulombs per second, and we use the symbol I to represent electric charge right here. Another way of representing coulombs per second, or units of coulombs per second, is that's equal to an ampere, which is abbreviated A. So 1 ampere of current is equal to 1 coulomb of charge flowing past some cross-section of a wire in 1 second. So back to this fact that it's the electrons that are moving. Remember, electrons, if there's an electric field applied to this wire by an external voltage source, a battery, electrons move against the electric field lines. So they'll be moving this way. But the convention is that electric current is the flow of positive charge. So we think about it this way. Even though it's the electrons moving and not the protons in solid state matter, if an electron moves to the left, it leaves behind a little bit of extra positive charge that's unshielded by an electron. So as the electrons move to the left, it's like positive charge is moving to the right. Conventional current is the flow of positive charge through a wire. So this picture is a circuit, an electric circuit consisting of a battery, which supplies a voltage. The battery has a positive terminal and a negative terminal, and a wire connects the positive terminal of the battery to a terminal on a light bulb, and then the other terminal on the light bulb, which is actually the part of the casing with the threads on it, gets connected to the negative terminal of the battery, and the light bulb lights up. So in this circuit, light bulb lights up because electric current starts flowing through the wire from positive back to negative. All right. So the convention is the current flows from positive to negative. What's actually happening is electrons are moving from negative to positive. But as the electrons move, like in the last slide, as electrons move counterclockwise, you can think of that as being equivalent to positive charge moving clockwise through the circuit. Okay, well, drawing circuits like this in this detail can be tedious, so let me introduce some notation for drawing schematics of circuits. Instead of drawing a battery, well, the symbol for a battery is 2 lines, where one is longer than the other. The longer line is the positive terminal, and the shorter line is the negative terminal. The light bulb is a device that uses electric energy, and in general, such devices are called resistors. And resistors have electrical resistance, R. The symbol for a resistor is a little sawtooth-like symbol that looks like that. And then we can connect the positive terminal and the negative terminal to the 2 sides of the resistor. So the battery supplies a voltage, the resistor supplies resistance to the flow of electricity, and a current flows from positive to negative in this circuit. So that's a simple diagram of an electric circuit composed of one resistor, one battery, and some wires. Ohm's law is the most important physical relationship to understand when it comes to studying how electric circuits behave. It's important, it's fundamental to understanding the connection between these three quantities: voltage, current, and electrical resistance. And so it turns out that if you hook up a light bulb, if your resistor is a light bulb and you hook that up to a battery, if you increase the voltage that's supplied by the battery, that'll increase how bright the light bulb shines. So that's a function of current. So in general, as the voltage goes up, the current goes up. On the other hand, as the resistance of the circuit increases, the amount of current that flows through the circuit decreases, holding voltage constant. So if you think about these relationships and combine them together, what you see is that there's a proportionality between current and voltage, and an inverse proportionality between current and resistance. And you put them all together and you get this relationship, which is called Ohm's law. It can be written in a bunch of different ways. Perhaps the most useful way is solving for V. V equals I times R. You could also solve for R. R equals V divided by I. Okay, so a little note on units. We know that the units of voltage are volts, and we use the symbol V to represent that unit. Current has units of amperes, and we use the symbol capital A to represent that. Electrical resistance has units of ohms, and the unit symbol for ohms is capital Greek letter omega, like this. Okay, so 1 ohm of resistance means if 1 volt is applied, 1 amp of current will flow. Okay, in the previous slide, we envisioned a circuit composed of a battery, some wires, and a resistor, like this. And we said that the resistor has resistance, the battery has voltage, and the current flows through the wires, the resistor, and through the battery. Now in the real world, so here what we're assuming is that the wires are perfect conductors of electricity. In reality, though, wires themselves also have resistance to the flow of electricity. It's just that usually the amount of resistance that the wire has is insignificant compared to the amount of resistance that other components of the circuit have, light bulbs, motors, that sort of thing. So we usually ignore the resistance of a wire, but sometimes you need to know how much resistance a wire supplies to the flow of electricity, and we have a theoretical equation that allows us to estimate this, and it looks like this. So in general, the resistance of a piece of wire is proportional to how long the wire is, L. This should make sense. The longer the wire, the more resistance it has to the flow of electricity. On the other hand, the resistance is inversely proportional to the cross-sectional area of the wire. And this should make sense as well. As the cross-section of the wire gets bigger, the resistance to the flow of electricity gets smaller. Oftentimes you can think of an analogy when it comes to electricity flowing through wires, and that analogy is water flowing through pipes. And so this makes sense that if you have a wider pipe, it offers less resistance to the flow of water. You can push more water through it. You can have more current flowing through the pipe. Same with wires and electricity. The fatter the wire is, everything else being equal, the more current you can push through that wire. It has less resistance to the flow of electricity. Then the other thing that matters is a property called resistivity, and this is a property of the material that the wire is made out of. So some materials like copper have very low resistivities. The resistivity is low. Other materials like glass and rubber have very high resistivities, meaning they're not very good at conducting electricity. Okay, so for a given length of wire, given cross-section of wire, and if you know what the material is made out of, you can calculate the resistance of a wire. We're going to use this equation in lab, so we'll get a closer look at this equation in lab. All right, so this concludes part 1 of this lesson on Ohm's law, and the next lesson we'll pick it up with looking at electric power and the difference between AC and DC currents and voltages.